Okay, so welcome everybody. Weekend. There's a little bit more math this week for us. This part of the entire course. And I was thinking a little bit about whether we should go into the details about the proofs or whether, you should just, take it up on faith that it's true. But I think there are a couple of basic theorems that are actually really worthwhile proving. We're not going to prove some of the more difficult ones, but at least we'll prove, for instance, a very simple version of a Chernoff bound, such that you can actually see how they work. And yeah, I hope that's actually going to be useful for you. So at least it should unfrighten you from using those things. And the convenient thing to do is usually if you need one of those bounds, first of all, you should know that they exist and that there's Wikipedia, and you basically look up the theorem and that fits your needs best and you apply it. So if you recall what we did last week, we looked at basically the central limit theorem, the law of large numbers, and so the weak law of large numbers, we basically showed that things will converge, and the way to go about it was by going through the characteristic function expansion. So in other words, we proved all things in Fourier space because things were a lot easier there, because they are limiting procedures, since convolutions to powers, you could actually compute that very easily. So that's how we got the weak law of large numbers, and then by taking the mean out, we basically got a polynomial expansion where only the quadratic term was left, and then again we did the same limiting procedure to show that for random variables with given mean and given variance. So the mean and variance have to exist. But in this case, the central limit theorem holds. And you could probably design similar things for higher order moments, subtracting out first and second order terms. The other surprising thing that we saw is that if we have random variables that are very, very well behaved, so basically indicator variables on the unit interval are very well behaved because they don't have very long tails, then already by adding 5 of them together, you got something that looked, pretty much like a Gaussian, right? I mean, at least if you didn't look too hard, you might think, hey, this is a Gaussian. And now what we're going to do, so this all qualitative rate behaviors, sure, with constants and so on, but if you then actually want to ask a question like, how many samples do I need, this doesn't immediately tell you how many samples specifically. It'll just tell you how your accuracy will grow as a function of the number of samples and, a couple of other properties. So in order to get finite sample size tail bounds, well, we need to actually derive them. And the simplest ones that you've probably already seen is the Gauss-Markov inequality and the Chebyshev inequality. Who's seen those before? Awesome. So that's about probably 2/3 of the class. Good. So proving them is ridiculously easy, right? So basically you prove it by first proving the Gauss-Markov inequality and then applying it to another random variable. So what it says is, suppose I have some random variable x with mean mu, and I want to upper bound. Any question? Okay. And I want to upper bound the probability that this random variable exceeds epsilon. Because epsilon can actually be less than mu, it could be larger than mu, but obviously if it was less than mu, then you wouldn't get the terribly useful bound. And well, that is by definition the integral from epsilon to infinity over dp of x. Right? That's the thing here. And well, since I know that this is less than, that all those numbers are greater or equal than epsilon, I can just go and divide by x over epsilon dp of x. Because this ratio will always be larger than x, right? Than 1, right? So if I multiply this by a number greater or equal than 1, it's still an inequality, right? So then I can go and pull the epsilon out and use the fact that I can now integrate from 0 to infinity. Let's, without loss of generality, assume that x is greater or equal than 0, otherwise It would be kind of stupid anyway. And that's just the mean. So I now get mu over epsilon. So in other words, the probability that x is greater than epsilon goes like mu over epsilon. What this means is if mu is really small, then I actually get a really tight bound for this. It's still not a very, very good bound because, I mean, it doesn't have very good scaling in terms of, well, how many observations do I need and whatever. But you can actually use this as a subroutine in designing a larger inequality that will use this. So for instance, if you take the minimum over several of those terms, then you will get an exponential guarantee as well, and you can get best paper awards by using that. And yeah, I mean, literally, so the count-min sketch basically does that. Any questions about the first inequality? This should be all very, very basic tools. Yep? Okay. Is x positive? Well, as a matter of fact, we don't really need to assume it, because this still holds if I integrate from, you know, something negative here. The only thing that could help, no, actually we have to assume that it's positive. I apologize. Otherwise it's nonsense here. Yes. We have to assume that it's positive. Good question. Any other questions? Any other question? No. Okay, good. So the next thing then is to use the Chebyshev, to get the Chebyshev inequality. And for the Chebyshev inequality, all we do is we just design a new random variable. And let's call y equals x minus mu squared. We know that the expected value of y is just sigma squared, because that's how the variance is defined, right? Now, all I have to do is, you know, set my new epsilon to be epsilon squared, and I'll get that the probability that, you know, y is greater than epsilon squared is less equal than sigma squared over epsilon squared. Right? Now, this is nothing else than saying that x minus mu here is greater than epsilon, right? Okay. So that's all right. Now, if we have a random variable x that is given by 1 over m, sum over I going from 1 to m xi, then what's the and let's assume that each of those xi's has variance sigma squared. What's the variance of x? What's the variance of x? Is it sigma squared? Who votes for sigma squared? Who votes for sigma squared over m? Who votes for sigma squared over m squared? Okay, I think the majority has it. So the variance of x is sigma squared over m. So now, plugging this in here, we get that, you know, this quantity here becomes that the probability that, and let's just call this superscript m, that superscript m x minus mu is greater than epsilon is less equal than sigma squared over m epsilon squared. Now let's solve this for delta. And what I get is epsilon is less equal than sigma times, and now here I have 1 over square root m delta. Right, because we have the delta here, we take it down there, move it over, and take the square root. So what's good about this? Well, at least we now have some guarantee where we know that as we average more and more and more, our uncertainty shrinks. But it doesn't shrink quite as fast as we would have hoped for. So basically, if I have 100 times as many observations, I only get 10 times the accuracy. So it therefore means that, you know, there's a very tight natural limit to, you know, how accurately you can get with limited resources. There's some other guarantees that will have a 1 over m behavior, but that will actually depend on knowing a lot of additional things about your distribution. The one thing that's really bad about this is that it actually depends on 1 over square root uncertainty. So in other words, if I want to have a really small uncertainty, let's say 1%, you know, this multiplies everything by a factor of 10. So this is bad news. The question is, can we get, so it's especially bad news, let's say I invoke this bound many, many times, right? And my probabilities add up. Then I pay the square root of that, you know, number of times that I invoke this inequality in terms of my guarantees, which is terrible. And afterwards we'll see that there are actually ways where you can get away with the logarithm of this. So the good thing is it has a non-trivial scaling behavior in M. The bad thing is that this bound is really bad. However, note that we didn't need to impose anything on the range of the random variables really for this to be well defined. All we needed is that a mean exists and a variance exists. And you might actually at some point, you know, try to do inequalities where you take this and combine it with, in, let's say, a Chernoff bound to get a more aggregate inequality which has Bernstein-like properties. And don't worry, we'll get to all those things in a moment without get full range bounds. So there's a very useful trick. So to summarize what I just said, so Gauss-Markov gives us epsilon is less equal than mu over delta. So it has a nice scaling property in mu, but okay. Question, why is there no sigma in the first inequality? Why is there no variance dependence in the first inequality? Any ideas? Well, very simply because I didn't assume anything about sigma, right? It's almost a trick question. But basically, usually the more you know about your distribution of random variables, the more you will be able to get tighter bounds. So therefore, if you want to get any guarantees, the first thing you really need to do is basically constrain the random variable that you want to estimate as tightly as you can with prior knowledge where you know that things will not be worse than something. And this can save you a lot of money in practice. So for instance, if you are doing hypothesis testing for, you know, displaying ads and so on, if you can have decent prior knowledge about how likely a particular ad is to do well, then you don't have to show it that many times to find out whether it's really good or not. Okay. And so, okay, so let's get the logarithmic scaling in delta. Any questions so far? So now we'll actually need to introduce something slightly new, and this is probably one of the more equation-heavy slides, but this is actually the simplest proof I've ever found for the Chernoff bound. And this is a very simple Chernoff bound, which only depends on binary random. So there are more general ones, which, you know, where the same statement essentially holds for, you know, real valued random variables with values between 0 and 1, and then also for larger ranges and so on. So much stronger results exist, but this is probably the simplest proof that I know. So the first thing that I need to introduce is the KL divergence between two random variables, in this case binary random variables. Who has heard of it before? Awesome. Okay. Who's heard of the entropy before? Not the bookstore, but the thing, right? Okay. So the entropy of a random variable, you can think of it as the minimum number of bits that you need to encode it, right? So in other words, if you give me the entropy, or if you give, or rather give me, the probability distribution, I can design a code for you that will, in the limit of, seeing many, many instances of this random variable, encode the entire sequence stream with entropy many bits per random variable, for instance. Okay. So your cell phone does something like that in a very clever way, and it uses turbo codes and a few other things probably. So lots of beautiful math there. Okay. The KL divergence, you can do this, and so this is basically our 2 minutes of introduction for this class, as the extra number of bits that you have to use by using a code that's not as good as the optimal code. So basically, the KL divergence is what would happen is if I gave you the wrong probability distribution, you designed a code for it, and then you went to encode data drawn from the true distribution, and so you'll end up wasting more bits than you should be using. And that's exactly what the KL divergence measures. Now, in the specific case where I have binary random variables, so they are basically 0, 1 random variables, and they are 1 with probabilities p and q respectively, then this is nothing else than p log p over q plus 1 minus p log 1 minus p over 1 minus q. So let me just write out the general definitions, because there's probably no harm in seeing them. So the entropy So the entropy of a random variable p, h of p, is given by the sum over x, p of x, log p of x. And if I use the natural logarithm, then you talk about the entropy in terms of nats. And if you have the binary logarithm, then you talk about it in terms of bits. Right? That's about the only difference. Okay. Then the KL divergence between two distributions, p and q, is given by the sum over x, p of x, log p of x over q of x. And you can immediately see that you can decompose this as the sum over x, p of x, minus p of x, log q of x, minus the entropy. Okay, so why would I write it down in such a complicated way? Well, remember, that's the number of bits that you need for the correct distribution. If I use the code that comes from q, I will need log q of x bits for encoding x. And so you can see that then the expected number of bits is this quantity here. This is the minimum number. So you can see this is exactly the excess number of bits. Okay. So, any questions about that so far? Yeah? So d of p and q is the Kullback-Leibler divergence. Let me write it out. Yes. Okay, so look this guy up on Wikipedia. There's probably 2 people. So KL divergence. And sometimes people write a funny double bar between P and Q. So there's, probably about 4 or 5 notations that I know of. Can somebody tell me whether who thinks P and Q is symmetric? Who thinks it's asymmetric in P and Q? Okay. And the rest is asleep. Okay. But it is asymmetric, and you can check that easily. You can actually symmetrize some of those things, and there's a lot of beautiful things that you can do. If you like this type of research, there's a wonderful book that you should read. It's by Thomas and Cover. And I think there's an H in here. It's just called Information Theory. I think by now both of them are dead. This is one of the most beautiful information theory books you'll find. It's a great book. Yes? Well, why am I going from here? How am I going from here to there? Well, the log of the ratio is just the difference of the logs, right? But why is it defined like so?
So when you are taking the difference between two distributions,
Yeah. Yes, but the thing is that I'm basically giving you the wrong code, and you're encoding the right distribution, namely the p distribution, with the wrong code. So that's why the expected number of bits by using the wrong code is sum over x, p of x log q of x. If it was the correct, otherwise, yes, comparing two distributions would simply be comparing the entropies in this case. But I want to know, for instance, how close those two distributions are. Because I could have, so let's take the extreme case. I have a distribution which produces heads with a quarter probability, and I have another distribution which produces tails with a quarter probability. And you can easily see that those two have the same entropy, right? They're just mirrored of each other. And if I just take the difference between the entropies, the difference will be 0. It's quite meaningless. I can just say, okay, yeah, they have the same entropy. But they are actually very different from each other. So to compute the difference, the Kullback-Leibler divergence is one way of going about it. There are lots of other techniques that you can use, where you can, for instance, define metric embeddings of distributions in Hilbert spaces and do a lot of essential linear algebra there. So Geoff has done awesome work in this context. But that's really very much a matter of what you want to measure, what guarantees you want to get. Okay. So now let's actually put this inequality to good use. And the inequality basically goes as follows. So this is the Chernoff bound, that the probability that the sum over a bunch of random variables, xi, and they're binary random variables, they're combined with probability, that they exceed q, that this is less equal than e to the minus in Kullback-Leibler divergence between q and p. And then there is a useful technical inequality called Pinsker's inequality, which shows that you can upper bound the KL divergence by this. Sorry, lower bound it by this. So this is the quadratic expansion that I showed you before. This, by the way, sort of forms the basis of Gaussian approximations of KL divergences where the two distributions are very close. So you can actually do a lot of really fun things with this. There are Hilbert space generalizations of this. But for our purpose, assuming that this holds, right? Now we only need to prove that this inequality is there. By the way, if you want to take this further, you can get what's called packed Bayesian bounds. And so David McAllister at TTI, he's been doing a lot of really, really nice work on this. But that would be definitely way beyond 10701. So let's just leave it there, and I'll leave it, and feel free to follow them up or ask me about it. Okay. So without generality, let's say Q greater than P, because otherwise it's kind of pointless, right? Because we want to upper bound, we want to, get a guarantee that this sum of random variables doesn't exceed the expected value, which would be n times P, by, a large amount. And, okay, so let's say that K equals greater or equal than Q times N, some integer. Okay. So the probability that the sum of all those xi's equals K, given Q, divided by the probability that this is equal to K, given that I'm actually drawing from P, is just that ratio. That's completely standard, right? Because, I draw K times Q, I draw, N minus K times, I end up, drawing tails, again, heads and tails, right? So this is correct. Now, since I know that K is greater or equal than Q times N, well, this is greater or equal than Q to the Qn, and correspondingly increase this. Same thing for the denominator. So all the modifications by switching from K to Q times N work out the right way. And that's all we really need to the Chernoff bound. This is really awesome. It's so simple, right? Because now all you have to do is you just realize that, hey, this is actually e to the n times the KL divergence between the two distributions. Okay. So what we now have is that we can upper bound the ratio between those two, lower bound the ratio by e to that quantity here. Okay. So now let's work out what the probability of excess is, right? So we need to sum over all the cases where K is greater or equal than n times Q. Because those are the only cases that matter. So plugging this in, I get that, this is less equal than the probability that I draw rather than from P, I draw from Q. And I multiply accordingly by that ratio that we got. It's just plugging this inequality in here. And then, of course, whether I sum for K greater or equal than n times Q, or whether I go and sum from 0 to n, that can only make this thing larger. So therefore, this entire sum here goes away. So I get 1. So I get e to the minus n times K L divergence between Q and P. And that's the entire proof. It's almost magic. It's such an amazingly simple proof, right? Any questions? And this proof is not obvious. And the initial proofs were not as simple as this. You could spend pages. Okay. Any questions? So if you, yep.
I don't really understand the first inequality, how when you change K to Q times N, how do you get that inequality?
Well, we know that Q is greater than P.
Okay.
And we know that K is greater than Q times N. So therefore, that first ratio here, right? Since I know that Q is greater than P, that ratio is greater than 1. So if I therefore reduce the exponent for that ratio, it can only get smaller, right? Conversely, I know that that ratio is less than 1. Because, well, Q was larger than P, so 1 minus Q is less than 1 minus P. And so now if I increase its exponent, it can also only make things smaller. So the first thing can only make things smaller, the second one can only make things smaller. So therefore, in combination, they also only can make things smaller, which is exactly what gives us the e to the n times KL divergence. Okay. And then, once we have that guarantee, all we do again, it's very similar to what we did with the Gauss-Markov inequality, right? You basically first, look at the partial sum, then you bound terms in such a way that it's convenient that exactly the dependency that you want comes out, which is this here. And then you say, well, okay, now let's just pretend we had the full sum, and you make that term go away. So that's why I went to the Markov inequality before, because we had that same trick where we first upper bound, and then we integrate. That's a very useful strategy. Okay. Any other questions? And thanks for asking. Okay. So the question is, how can we assume that Q is greater than P? Well, you can't really. But what you can do is, okay, so get upper bound, right? And well, in upper bound, getting a guarantee that it's not greater than its average, that doesn't really help very much. But what we can do is, if we want to get a smaller Q, we just flip things. So we turn heads into tails and tails into heads, and that's how we get the inequality from the other side. And so this is how you get one inequality from the top, one from the bottom. So if you want to get a deviation inequality that tells you that the empirical average isn't going to deviate much from its mean, you just combine those two inequalities, and you have, overall bound that tells you you're not going to deviate by too much. So this is why I was able to get away with Q greater than P. Good question.
What I'm trying to say is that this won't be what's the opposite of tail, right? Like it won't let you bound how much mass is in the center. It only lets you bound how much mass is on the tail away from the mean, or the bottom tail away from the mean.
Exactly, and that's why those things are called tail bounds. And typically, this is what you're worried about, right? You're worried about seeing, too many unusual observations, right? This is essentially what caused the stock market to crash, because everybody used the Gaussian copula. They assumed independence where there was none. Fairly well-behaved Gaussian models, and that's what wrecked everything. Because then when one thing started going bad, all the other things that were correlated with that also went bad. So basically, this was bad math and bad independence assumptions. Question?
So this is only hold for binary variable?
So, okay. So thanks for asking for the next slide. So what we did is we proved the super simple and easy case for binary random variables. However, this theorem is much more general than that. And one way to generalize it is what's called McDiarmid's inequality. This is probably one of the most useful inequalities that I know of. There's actually a follow-up by McDiarmid and Reed. It's fairly recent, from 2005. And so this is actually a superset of this, and it contains self-bounding inequalities that let you do clever things when you have variance guarantees and so on. And yeah, so but I mean, for the purpose of this class, this is about as technical as we're going to get. So if you think about the average, right, this is a function of many random variables, and it has this property that if I change one of them, the rest doesn't, the average doesn't change too much, right? At least if the random variables are bounded, and changing one of them doesn't change the average by too much. And what McDiarmid did is he realized that there is a general property of random variables, namely that if I have some function of them that doesn't change too much if I change one of its arguments, and those functions don't have to be symmetric, they can be anything. They can have things interacting in all sorts of bizarre ways, but as long as that holds, then I can get what's called concentration of measure. So concentration of measure simply means the tails aren't too big, and the typical case is actually not much different from the worst case that you're going to see. That's what concentration of measure tells you. Anyway, without too much ado, the the guarantee goes as follows. If I have some function that doesn't change too much if I replace one of those variables, and not changing too much means it doesn't change by more than ci. So this is like, like a bounded range constraint. And define c squared to be the sum of the ci squares. Then the probability that the function deviates much from its expectation is bounded by 2e to the minus 2 epsilon squared c squared. So more to the point, if we actually assume they all have bounded range, and we just take an average, we get exactly the Höfting inequality out of it, which is a slightly more general case than what we proved on the previous slide. And yes, this is a lot more work to get. This is probably, 4 or 5 pages of math. So we're not going to go through this.
So strict generalization, right? Because it assumes bounded range, whereas Chernoff does not.
So Chernoff assumes that we have binary random variables, 0, 1s. Okay. So that's even more restrictive because I only allow 2 different values. However, Geoff is right, it's not a strict generalization because here I have a KL divergence, right? So there are KL divergence-like inequalities of that form, and you would have to search for that. And as a matter of fact, for uniform convergence theory, you can also get KL divergence-like inequalities, which is exactly what this gentleman here did. This was quite a breakthrough. And yeah, so I just wanted to show that this is actually very powerful because you can use it to engineer very quickly an inequality of that form. The other reason why I wanted to show you this is because we will actually use it later on in this course, either today or tomorrow. And that'll be then the most difficult promise that we'll go through in the entire class. It'll be 1 slide with 6 lines of math. Yep.
So here you change the xi, the change it at this time, or you can change it as much as you want?
So I can change it as much as I want as long as I don't change it by more than c. So I'm assuming that the xi's are between 0 and c, or they have some range c, and so therefore, if I replace one xi by another one, their difference cannot be more than c, and so therefore, they cannot contribute to the average by more than c over m, right? Because I'm taking an average over them. Okay, let me show you. So let's say we have 1 over m, sum over I going from 1 to m xi. And so this is my function f. And I subtract from that 1 over m, sum over I going from 1 to m I not equal to j xi, and have this plus some xj prime, right? Absolute value. Then I can see all the terms cancel out, and I get that this is nothing else than 1 over m xj minus xj prime. Right? Now, if I know that this here is less equal than c, I know that this is, less equal than c over m. So therefore, capital C, which is the sum of those squares, capital C squared, is nothing else than little c squared over m. And then plugging this back in here, we get Höfting. So does that help you a little bit?
So how about like
So
Above, you can change x as much as you want as long as it doesn't change the output of f, right? So there's a bound on the change in the output of f.
yes. So for instance, if I had something like 1 over 1 plus x squared, you could see that the output of that function would not be more than, change between more than 0 and 1. So now I can have x take on all the values that I want. As long as it cannot affect the outcome too much, it's fine. This is one of the really nice things about that inequality. And we'll later on see a very, very crazy function of those random variables. Yes?
How do we get C given a function?
How do we get C? That's a really good question. You look at your random variable and you decide, okay, that's the bound. So for instance, if I have probabilities, we know that they're bounded between 0 and 1. If I have classification errors, well, they're bounded between, let's say, 0 and the maximum cost that you will incur by misclassifying things. So it's really a function of whatever you know about your problem. There are some cases where it's unbounded, and then you have to do a lot more work to get something useful. Any other questions? Okay, good. So let's actually use this, because we'll get something rather cool here, right? So let's say delta is the probability that I will deviate from my mean by more than epsilon. And okay, so we get that this is less equal than 2 e to the minus 2m epsilon squared over c squared. So now you solve for that, right? So you take the log, and you get that the log of delta over 2 is less equal than minus 2m epsilon squared over c squared. And then if you solve again, right, you get that epsilon is less equal than c. So that's a good thing, because at least those two things scale in the same way, right? This is the bounded range. This is the accuracy. So epsilon over c is like the relative accuracy. And then here I have a log 2 minus log delta over 2m. So we get the same 1 over square root scaling that we had before, 1 over square root m. And furthermore, we now have a logarithmic dependence on the probability that something can go wrong. So with this inequality, I can go and, for instance, test maybe 1,024 times, and I only pay a factor of 10, right? Because that's basically. So this is much better behaved than whatever we had before, where before things would, well, a lot. Yeah.
So what the point here is that we're thinking of using the union bound. So if we want to get a low union bound using a lot of different tests, we have to set delta very small for each one of those tests, right? And then the fact that we only pay logarithmically in delta means it didn't hurt us at all to set delta small.
And we'll go through a couple of those union bounds, basically when we look at uniform convergence guarantees for function classes. In other words, trying to get a handle on the difference between training and test error. So there's one more tail bound that's probably useful to know, and that's called the Bernsen inequality. And okay, so I don't expect you to remember all those inequalities, right? So that would be crazy. What I expect you to remember is that there are different types of these inequalities. You vaguely remember at least one of their names. You have some idea of how they kind of sort of scaled, and you know to look up the explicit constants, in your math book or in Wikipedia or on the slides or wherever. So the interesting thing about the Bernsen inequality is that it actually has, at least in some regions, a faster convergence behavior. And we're not going to go into this in a lot of detail, but basically, if you look at this inequality here, this is again an equality empirical average greater than true expectation by more than epsilon. And we have the usual minus, t squared over 2 bound. So this is like, okay, this actually should be epsilon, sorry, rather than t. So do a query replace in your mind. And however, what we have in the denominator are two terms. One term, which is essentially the variance. And there's another term that's essentially, a range bound, almost like a mean. Right? Now, two things can happen. If you look at the denominator, it could be that, the first term is relatively large, or it could be that the second term is relatively large. Right? So for very, very, very small t, or epsilon in this case, obviously the second term in the denominator will never be large. And then we get something that has a look and feel very much like a conventional, Chernoff bound that we had before. So we had basically, t squared over range squared. However, when the second term is large, which can happen, for instance, if you have very small variance, so that can happen, for instance, if you have a pretty good idea of what you should be seeing, then the t in the numerator and the t squared in the numerator and the t in the denominator, well, they cancel one of those t's out. So now in this case, we get a rate of convergence that initially goes more like 1 over sample size if you work out all the math. And only later on, as you converge to the thing that you actually want to compute, your rate of convergence slows down to 1 over square root n. So you have this very interesting behavior where as long as you don't want to get the answer quite that accurately, you have very fast convergence property. And then only later on, as you get very close to the correct numbers, then it's pretty much an averaging procedure. That actually has practical consequences. So let's take 2 classification problems. Let's say we have one here. Anyway, basically you want to separate squiggles from something that looks kind of like a triangle. And what you see is there's this region where there's basically no data. And if there is a region where there's no data and things are nicely separated, then you can actually get the order 1 over sample size rate of convergence. Whereas if you have a problem where there's a lot of data in between and it's sort of intermixed, then in order to find out where exactly that boundary should be, right, you pretty much need to average and you need to wait for a long time. And this is where you then get the 1 over square root m convergence. This is actually well known under a name called the Subic margin condition. And it basically measures how noisy things are close to the decision boundary and how much data you have there. So if things are very, very smeared out near the boundary, it'll take you a long time to find out exactly where the optimal boundary is. Whereas if things are very clear-cut and there isn't much data in between, in other words, when the problem is easy, then you don't need a lot of data to figure out what's going on. And there's a lot of those inequalities. So don't be intimidated if you read a paper and it goes like, and yes, we generalize the Azuma inequality, whatever, whatever. Don't be scared. Just look up the bound and you'll be fine. It's just various technical conditions under which certain slightly tighter results hold. The general flavor is that you either get the 1 over square root sample size or a 1 over sample size rate. And that depends on how easy the problem effectively is in the limit. So in the Bernsen inequality, m would be an upper bound on the random variables. That's more a mean-like quantity. And well, the first term looks very close to a variance, right? So, I mean, you can easily see, one is, scales linearly with a random variable. The other one scales quadratically. So the ones that scale quadratically are more variance-like. And I mean, it doesn't really help much beyond intuition to, squint at that and try to find a deeper meaning in the t over 3 part or something. But yeah, what's important is that you get an intuition. So with that, let's actually put them into practice. So I'm now going to go through a case that you might very well have if you do an internship with a startup and they want to redesign their website. Any questions so far about the math, because we're going to use it now? Yes? 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 So when I derive McDiarmid from, well, I cannot derive McDiarmid from Höfting or Chernoff. McDiarmid is stronger. But, well, if I have a binary random variable which takes on the values 0 and 1, then C equals 1, right? Because that's the range of that random variable. Right? So this makes it really easy. And then I can just, plug that in and, right. So, well, if I take an average, so then I get, 1 over m, because the values can only change by at most 1. If I have, the difference between something that has a value of 0 and 1, and another thing that can have the values between 0 and 1, then if I change one of them, things can only change by at most 1, right? If I divide that by m, it can change by at most 1 over m. Summing those up gives me, again, this 1 over m bound. So maybe let's go through some practical tail bounds, and then we'll see what happens. And yes, this is taken from an A/B testing for website masters page, so I didn't make this up. So let's say I have 2 web page layouts, and I want to find out which one's better. So what I can do is I basically, on my server front end, have a small random number generator, and have the users, maybe all the users where the cookie, the most significant bit is set to 1, get to see version A, and all those users where the most significant bit in the cookie is set to 0 get to see version B. This is actually pretty close to what people do when they deploy new algorithms, except that they don't really go and, for instance, if you are in a search engine, you're not going to try out your new algorithm on half the entire user base first. You might try it out on a very, very tiny sliver, right? Maybe, 0.1%. Because if you screw up, you've still annoyed a lot of people. Let's say you have a billion users. You've still managed to annoy 1 million users if you screw up on 0.1% of all users, right? So you don't want that. And that might actually cost you real money. So this can be expensive if the algorithm doesn't work. Anyway, so let's say we do this. And then the question is, how many trials do we need to decide which page attracts more clicks? And so to make things a little bit more concrete, let's assume that the probabilities are P of A is 0.1 and P of B is 0.11. And furthermore, I'm assuming that P of A is actually known. So that's the setup. Any questions about the setup? So I want to know what P of B is, or more to the point, I need to know how long I actually need to test before I can say, well, P is really better than A. And so what I need to do is I need to identify at least a deviation of 0.01. But we don't know yet that P of B is 0.11. But what we want is we want to have a failure probability of 5% at most. So with 95% confidence, I want to be able to say that P of B is better than that B is better than A. So let's just use the Chebyshev inequality, right? That's about the simplest thing we can do. Let's say we have no prior knowledge and we can only bound the variance, therefore by bound it to be 1/4. We know that the random variable is bounded between 0 and 1. And so, okay, so I get m is less equal than, sigma squared over epsilon squared delta. Right? So sigma squared is 0.25. epsilon squared is 10 to the minus 4. Delta is, 5%. And plugging this all in means that I have to test it on 50,000 users. And after 50,000 trials, I'll know which one is better. Okay. Now, if we know that the probability is, at most 0.15 for design B, which is a sensible thing, because maybe I actually want to have a lot of clicks anyway, so this is quite a sensible thing to do, then I know that the variance, is a bit lower, so it's, 0.1275, which means that all of a sudden now I only need 25,500 users. So just by, assuming additional things about our random variables, have I managed to reduce the cost for the experiment by half, which is kind of cool. Okay, so let's do something better. Any questions about that so far? Yeah? By 0.25, that's just because I have a binary random variable, right? So I just compute the variance. So let's do that. So I know that the expected value of a 0, 1 valued random variable is p, right? Now I need to compute p times 1 minus p squared plus 1 minus p times, well, in this case, p squared, right? And then you maximize this over choices of p, and you'll see that, the largest variance is exactly for p equals 1/2. You plug it in and you get that. Right. So then, you get 1/2 to the power of 3 plus another 1/2 to the power of 3, which is exactly 1/4. Yep.
The 0.15 probably based on your knowledge of A.
That's based on on an assumption about B. So, for instance, if I, roll out a new ad campaign, and I know my current ad campaign is doing well, then, and I've already done a fair amount of work, then it's a reasonable assumption to make that my new ad campaign, while it might do better, which I hope, isn't going to have 100%, click probability, for instance. So it's not going to be insanely awesomely good, but it's just going to be maybe a little bit better. And that helps me a lot. Usually it's a bad idea to bound it away from 0, because while I might think that it's good, it might be spectacularly bad, and, well, I'll only find out once I run the experiment. But this is basically what you do. What actually happens in practice is often a little bit more insidious. So this is a problem we ran into recently with some real experiments. So we looked at a new recommendation system, and in all of our tests it actually worked really well. And then we deployed it, and the first day, of course on a small test sample, and the first day it worked really well, the second day it worked worse, the third day it worked even worse, and steady state it worked worse than the previous system. Does somebody have an idea of what might be going on there if I'm showing ads? Basically, which assumption is violated if something like that happens? Independence is violated, correct. Can you be more specific about what might be happening in this case? So the users are very, very, very good. The users are probably being shown the same ad more than once, so you get user fatigue. So in other words, the users actually have a memory of what they've seen before. You're not just showing the ads to goldfish, but to humans. And if they didn't click on something before, then, well, maybe the next time isn't going to be so different. So this is effectively what happened. And yeah, so at that point, once you diagnose what the problem is, you need to come up with a more refined statistical model, and then you can actually fix it. So this is why in practice often those assumptions aren't quite so correct. Okay, so now let's apply the Höfting bound. And okay, so we have random variable with bounded range between 0 and 1. We solved the inequality from Höfting, right? So we have c squared, which is 1 over log delta over 2 over 2 epsilon squared. So we get the same thing here. And now all of a sudden we get 18,000. So just by using better math, we save money. Okay. Now, this is about as far as it gets if we don't make any stronger assumptions. However, what we could do, and this is now an approximation, it's not a bound anymore, but in practice this is what you would be doing. You, for instance, assume asymptotic normality. We then take a Gaussian interval containing things with 0.95 probability, right? So if you know what that range is, right? You see that, you know, a deviation of, you know, at most 2.96 standard deviations gives you that 95% confidence interval. And then you plug this in here, so you get, you know, this times the variance squared divided by epsilon squared. We get a better guarantee on the variance. We take the more accurate guarantee on the variance. And this now gives you 11,000 trials. So that's a lot more usable if you think about what we're trying to accomplish. As a matter of fact, this is pretty close to what you would hope for, because remember our convergence went like 1 over square root sample size, right? It's about 10,000. So 1 over square root 10,000 is about 0.01. We wanted to get to identify a distribution that's 0.01 away, and we need a little bit over 10,000 observations. There's not much more you can do beyond this. We've really squeezed it all the way we could here. But we've gone down from about 50,000 to 11,000, and this stuff is still quite reliable in practice then. I could be wrong. I could be wrong. Well, yeah, but basically you need to have ERF of 2.5% on each end. So that's, I think, what gives you the larger interval. Okay, so well, what do you do beyond that? Well, in practice, of course, you don't only have 2 experiments. You have many different layouts. You might combine layouts, actually have dependent random variables over which you want to jointly optimize. You will have statefulness, and all those things actually make those inequalities a little bit less trivial in practice than what I just showed you. But for simple web designs, this is actually the way to go. And you get the same thing, for instance, for drug testing, for chip manufacturing, and all that. So here's a really, really sad story. So I heard that from Dave Madigan. So Dave Madigan is a statistician at Columbia, and he essentially looked at the efficiency of drugs for various diseases. And then there are various experimental studies that people have done, and you can basically come up with different mechanisms for finding out whether some drugs help or whether they hurt. And he tried out about, I think, 10 different model selection techniques for, those basically confidence selection techniques for, a couple of dozen drugs. And unfortunately, the ranges of harmful to beneficial are sometimes both present for the same drug, depending on which test you use. And this is actually quite dangerous, because if you're a drug manufacturer, of course, you sell the thing, so you're going to pick the test for which your drug is considered beneficial, and then maybe somebody else who doesn't want that drug will use another test. So this entire area is not as reliable and stable as all those theorems suggest. In practice, when you have finite amounts of data and often not quite enough data to really make strong confidence statements, you will end up with the I don't know answer more often than you want. So don't try forcing statistics to do what it's not, where you simply don't have enough data, even though somebody might have a very vested interest in it. So have a look at his work if you're interested in this. Okay, so now we're going to put this to good use for learning theory. And I think we'll have just enough time to get the basic idea across, and we'll do all the math on Wednesday. Okay, so remember, we have some, after all, this is the reason why I, went through all this stuff with you. So we have some training data that's, let's say IID from some group. I have a loss function which tells me, how well I'm doing. I have some function class, and I want to solve let's say an empirical risk minimization problem. In other words, do as well as you can on your training set within that function class. Sometimes we write this as a penalty up here, but that's equivalent to doing this. And then afterwards at test time, well, this is, you get the real distribution. So as you've already all experienced in the homeworks and in the leaderboards and so on, the difference is really that, this is now the real world distribution. In our case, it's the Carlton distribution, right? And this is your homework assignment distribution. And you want to make sure that this is close. So you've experienced that quite amply. So let's say, for instance, I have some data here like so. Then if I take a crazy high degree polynomial, well, of course, I can fit it perfectly. And you would all agree that this is garbage. Okay. Here's what I can also do, right? I can take a linear function. And that linear function will, have, very good proximity between training and test error. But it'll be also quite horribly wrong. It's basically not going to be able to solve this. A quadratic function in this case, and if I threshold it suitably, will do just fine. So it'll pick out exactly the interval of minus ones, and it'll find the plus ones out here. So what I guess you've seen so far is, let's say we plot model complexity versus error, and this is a very qualitative display, as in this is really just, model complexity in some arbitrary complexity units, like normal function class, number of basis functions, whatever. It doesn't really matter. Some norm. And this is what you would typically see with a training error. As you make your model more and more and more complicated, well, the error will go down. It's typically not going to be as smooth as this, right? You may actually have, well, in some cases it may be as smooth as this, but typically it'll, have some jumps in it, but unless something is very wrong with your inference algorithm, it will not go up as you increase the model complexity. Right? If that happens, you know that your algorithm is broken. Okay. And then this is what happens with the test error. Right? It'll start high, just like the training error. It'll decrease, and typically it'll always be a little bit above the training error. And then there's this Goldilocks region where the test error is small, and as we make things more complicated, well, the test error will keep on going up again. Trouble is, we don't have the green curve. We only have the red curve, and we have this axis. We can sort of kind of guesstimate what the green curve would be without really knowing it. And this is what statistical learning theory does. It's one of several tools that you can use. So big disclaimer, and, well, the big disclaimer is really, well, that, I wrote probably my fair share of papers on this. Do not use this in practice too much. There are other techniques that work better in practice. However, in order to understand how the overall scaling behavior goes, so learning theory is awesome for qualitative results. It's awesome to know how rates should behave, how you should analyze and view problems. For specific instance, it's a little bit less of a fun thing. So if that serves as an indication, there was more than one NIPS workshop on uniform convergence bounds with probabilities less than 1. In other words, a workshop on theorems that have non-trivial predictions. That tells you about the state of the art in this area. It's not easy. Okay. Yep.
In the previous slide, yeah. So why test error should increase after certain
Well,
model complexity if your model is the right model?
well, because of that, right? Solve this perfectly is in the model class, right? But I have noisy data and I'll just end up overfitting to the noise. Well, the linear classifier, the constant would do nothing particular. It would just, put everything into one or the other class. So yeah, but basically, no, but yeah, I mean, these are the labels, right? This is just, a one-dimensional classification problem. So the classifier needs to find, this is the set of -1s, these are the sets of 1s. So the constant classifier would do something even more horrific. But yeah, I could fit a constant classifier, it would just not do me much good. Okay. So let's just see a little bit what happens here. So let's just go back to that plot because, yeah, it's kind of important. So one thing that you should notice is that as the model complexity increases, this gap typically widens. It doesn't necessarily monotonically widen, but it typically will widen. And that has a lot to do with the fact that if we have a very complex model, we had so many things that we could try out, and we need to basically get good guarantees for all those things that we could have possibly tried out, that it's actually non-trivial to get good guarantees. So now let's actually go through the math a little bit. So, here's a somewhat broken, and we have, let's say, binary loss. So we have 0, 1 loss, and I could just, take the optimal function that minimizes the empirical risk, and invoke my machinery. And I say, well, okay, I now have f star, and I get some loss that's induced by that. And then I just apply Höfting's inequality, and I get some rather nice and tight theorem, right? So no dependence on, model class and all that. So does somebody have an idea what went wrong by doing just this? Because, after all, it's a function. I can compute the training error. I didn't have to. Why doesn't it work? I mean, it doesn't work, that's clear, but why? What's wrong? Okay. Hint. Is this function f star just any arbitrary function? Okay, how did we get f star? Okay, any suggestions about what could be broken? So when you do your homework assignment, right, and you implement that code, do you upload just any arbitrary random function f, or do you do something more systematic? Yes, you upload it on, yes, you apply it to the test data, but more than that, you actually searched among a large pool of functions in order to get this f star. So there were maybe 1 million different functions that you could have tried, and you picked this function, maybe function number 529, and that's what you upload. That's what you use. Now, implicit in that is that you actually, your optimization algorithm in a very clever way looked at all the other 999,999 functions that you could have also uploaded. You picked this one in 1 million. So therefore, this function f star isn't just an arbitrary function. You've already effectively evaluated and discarded all the other functions that you could have uploaded in its state. So that's why, this simple bound doesn't work. Because, well, the Höfting inequality talks about a single test. What you've done effectively is, performed a million different tests and then, uploaded it. So let's make this a little bit more explicit. So what I've done here is I've tossed an unbiased coin 10 times, right? And, well, so let's treat this like, like a training error or whatever. And actually, all those strategies are equally garbage because they perform at probability 1/2. So you can see the number of counts here going from 3 to about 7. And if I wanted to, find a strategy, let's say I would pick strategy number 15. But of course, in expectation, it's going to be, 1/2. If I was to toss the coin, 100 times, you can see the same effect, but now things are varying quite a bit less. So in a way, we are onto something here, right? The thing that we're onto here is that if I have a lot of data, I can actually evaluate a lot of things, and then they won't deviate from each other by too much. If I have very little data, then asking 20 different questions essentially may already not be such a good idea. So what we, in other words, have to account for is the fact that we performed multiple tests and didn't have that much data for each of them. So basically, for each function in my function class, when I train, I invoke this machinery. And I decide, well, no, that's not it. Let's pick the next one. I mean, this would be the most stupid learning algorithm you could imagine, which enumerates all the solutions and goes through them one by one and discards them until it finds the best. Okay. So in other words, picking the best out of n gives us n opportunities to get it wrong. So now, if we want to have a total failure probability of delta, we therefore need to have a failure probability of delta over n per function. Right? And so what we do is we take our regular bound, right? So this is what we had. So we have, epsilon less equal than L square root log 2 over delta divided by 2m. And I now change delta to delta over n. So this becomes epsilon less equal than, so this bound then holds for all those n tests in uniform. That's why it's called the uniform convergence bound. We have now log n minus log 2 over delta divided, plus 2 over delta, right. So what this bound now is it tells us that, okay, here we have it, that now this inequality holds the functions. So if my learning algorithm has only a finite number of functions in it, let's say, for instance, I could have a learning algorithm that looks at each coordinate separately and just goes with the sign of that coordinate. So then if I have a 10-dimensional data, then the function class has 10 entries. Or I could go and quantize things, right? So what we have now is that the error is bounded by the empirical error plus that confidence. So this is the first non-trivial uniform convergence bound. So what we see is the the size of my function class enters logarithmically. It also depends logarithmically on the failure probability. And then it goes like 1 over square root sample size to get the accuracy. Okay. So I'll leave it at that. And so basically, the key questions that we're going to address on Wednesday is, well, what happens if this function class is not discrete? And let's say, what happens if we don't have a binary loss? If we have, let's say, a binary loss, or if we don't have a binary loss, you know, what things can I do to refine things? Okay. And we will conclude uniform convergence theory and learning theory on Wednesday. Don't worry. No more learning theory this week. Fun?